Oh, there it goes. It's working. Great. I've just messed up the angle a little bit. Okay. So that's a basic example of summation notation. Right? Is that this sigma sign means you're adding things up. The number on the bottom is wherever you start. The number on the top is wherever you end. So if I had something like this, where there's an n on the top, that means I'm going to keep going until I get to n. Right? So I'm going to start with, yeah, so let's say it's I cubed this time. So I'm going to start with 1 cubed. Then I'm going to do 2 cubed. Then I'm going to do 3 cubed. And I'm going to keep going until I get to n. And I'm going to stop with n cubed. So if n is 3, I just stop here. If n is 4, I'm going to go one more term. If n is 5, I'm going to go one more term. N is 6, I'm going to go one more term than that. So if there's an n on the top, it means how many things I'm adding together is going to depend upon what n is. That's the idea with summation notation there. Any other questions about that notation, what it means, how I'm using it there, before I go on to some more complicated stuff using it?
Would you ever use it with negatives?
Yeah. Yeah. If I put a negative sign in front of there, then you do a negative sign in front of this one, negative sign in front of this one, negative sign in front of this one, negative sign in this one. So then you're adding together a bunch of negative numbers.
Yeah. I mean, could I be negative 10? And you just count integers?
Oh, I see what you mean. Like this.
Yeah.
Yeah, I've seen people do this.
Right.
Usually I won't. But yeah, I've definitely seen people do this. So, and certainly in this course, we won't have to worry about any negative ones. But yeah, I've totally seen people do that in other more advanced stuff. What you will not see is you won't see this number being bigger than this number. That sort of doesn't make any sense. You won't see I equals 3 to 2. Yeah. So, the next thing I want to talk about with this summation notation is to actually go back into where I left off, well, not where I left off, the part I skipped in section 5.2. And the idea, there we are, so 5.2. So the idea is, where is it? There we go. So the idea is it turns out there's a bunch of laws of summation notation, which are useful for evaluating the sums. I'm not going to ask that you memorize any of these guys. I feel like memorizing these sorts of, well, at least not at this point of the course. Maybe, I'll talk about this a little bit. This stuff will come up again at the end of the course. We talk about sequences and series. And at that point in time, I might want you to be able to sort of work with this a little bit more in more depth. For now, these formulas, if I ask you a question like this on a quiz or a test, these formulas will all be on there so that you can use them. In fact, to be honest, the specific questions that will come up here are more likely to be assignment questions and quiz questions. But the idea is that there are these different laws of summation notation. And what they say is this. If we're trying to add, let's say, I equals 1 to 5 of 3, that means we're going to start with I equals 1, we're going to stop with I equals 5, and every time we're going to add 3. So we're going to do 5 terms that are all 3s. What does that give you? That gives you 15. Where did this 15 come from? It comes from this 3 times this 5. Actually, I'm going to write it as 5 times 3. Because then it's an example of this law. So if we add from I equals 1 to n of some number, c, the result's always going to be the number n up top times the number c. So if we add from I equals 1 to 5, 3, we're just going to have 5 3s, 5 times 3. Okay, so that's sort of the first rule of summation notation. The second rule of summation notation comes from if you have something like this. If we're trying to add 3i squared for a bunch of different things. Well, we can think about it as going to be 3 times 1 squared plus 3 times 2 squared plus 3 times 3 squared. Right? We can also think about this as 3 times 1 squared plus 2 squared plus 3 squared. That 3 that appears in all three terms can be taken out front as a common factor. And so this can be written as 3 times the sum I equals 1 to n of I squared. So the sum I equals 1 to, I equals 1 to 3, sorry. So the sum of 3I squared is the same thing as 3 times the sum of I squared. Right? This is sort of an example of this second law of summation. There's a third law of summation, which I'll do over on the far board there. If we want to do sum I equals 1 to 3 of I plus I squared, right? We can write it as 1 plus 1 squared plus 2 plus 2 squared plus 3 plus 3 squared. Right? That's sort of the basic way of writing it. Then we can sort of split those up. I can think of it as 1 plus 2 plus 3 plus 1 squared plus 2 squared plus 3 squared. Writing all these guys together and all those squares together. So that means it's the same thing as the sum I equals 1 to n of I, right? 1 plus 2 plus 1 to 3. Right? This is sum I equals 1 to 3 of I, is 1 plus 2 plus 3. This part is a sum I equals 1 to 3 of I squared. Alright, so that's what this law says. Is if we're adding together one thing plus another thing, we can add together those two things separately. So this is an example of this second law. This third law. This fourth law is basically the same as that third one, except all these pluses are replaced with minus signs. Right? We replace this plus this plus this plus this plus all with minus signs. This will become a minus sign. This will become a minus sign. And this last one here is actually this formula for the sum of an arithmetic series. I don't know if you remember. And again, it's something that's supposed to be covered in high school math, so hopefully you've seen it at some point, sort of arithmetic sequences, arithmetic series. This is one of the formulas from that. I'm not going to really have time to go over where this formula comes from in detail. These are the ones I sort of am more interested in because these ones are the ones that are actually going to come up again when we talk about integrals. Or these first sort of three properties. But, yeah. But those properties are things that are going to allow you to work with summation, are going to allow you to manipulate sums. Okay. So any questions about these properties before I show you how you can use them in doing an example like example 4? Okay. So example 4 here, we're trying to compute an integral. Right, we're trying to compute this integral. The key thing to mention is we have a method of taking an integral and turning it into a sum. That's one of the things we talked about last class, right? We replace the integral sign with this, right? The limit as n goes to, sorry, I don't know why that infinity looks like an 8. It's supposed to be infinity. As limit as n goes to infinity of the sum I equals 1 to n, right? We replace the integral with that. We replace the x with an xi star, and we replace the dx with a delta x. Right? I don't know if you remember this. I said, you know, how can you express an integral as a limit of Riemann signs? We can do it this way. Now, of course, in order to complete this procedure, we're going to need to know what delta x is and what xi star is. Delta x is always b minus a over n. B and a are the limits of integration here. So b is 2, a is negative 2. 2 minus negative 2 is 4. So my delta x here is going to be 4 over n. My xi star is always going to be a plus I times delta x. The a here is negative 2, I times 4 over n. that gives you negative 2 plus 4I over n. So using those formulas, we can actually come up with a better formula for this guy here, for this integral. I'm realizing folks over there are having a really hard time seeing this one. And I'm realizing I really just don't like the layout of this classroom because I like being able to use, having these formulas up on the screen while I work out stuff on the board, but that's not working out. You know what I'm actually going to do? That way it's not blocking anything. And the formulas are still there. And yeah, I'm just going to erase this stuff. Yeah. Okay. I think in this classroom that's actually, well, yeah, I was going to, there we go. That might be how I maybe in this classroom. With the middle board as like a projection screen. Okay. So what we've done is we found a way to write this as a limit of the sum. We found a formula for delta x, a formula for xi star. We want to plug those formulas into that limit. So here we have the limit as n goes to infinity, sum I equals 1 to n of 2 times xi star, which is 2 plus 4I over n minus 1 times delta x, which is 4 over n. Now this is an annoying sum to evaluate, but we can actually evaluate this thing using all those formulas. Yes?
X star, I think you're missing a negative by the 2.
Oh, thank you. Thank you. That 2, yes, was supposed to be negative. And that, there. Okay. So, we can multiply this thing out. 2 times negative 2 is negative 4. 2 times 4I over n is 8I over n minus 1, all times 4 over n. Now we have the limit as n goes to infinity. Sum I equals 1 to n. Negative 4 minus 1 is negative 5 plus 8I over n, all times 4 over n. And then if we simplify this, negative 5 times 4 over n is negative 20 over n. 8I times 4 over n is 16I over n. N squares. So I just simplified this complicated thing inside there to make it as simple as I can. And here's the point at which I pull out all these things that are on the board. Right now we have a sum of something plus something else. So we can write out what the something is and the something else is separately. So we will end up having the limit as n goes to infinity will still be in front. The first thing will be the sum I equals 1 to n, negative 20 over n. Yes?
I think it's supposed to be 32I.
Oh, thank you. Oh, thank you so much. I think thank you. Yeah, that's 8 times 4 is 32. I don't know how I got 16. I wasn't thinking. I'm clearly not thinking today. Anyway, so the first one is 20 over n. Then we're adding together 32I over n squared. Now, adding together 20 over n for all those i's is an example of this rule. We're adding together a bunch of numbers that are all the same every time. Right? When I is 1, this is negative 20 over n. When I is 2, this is negative 20 over n. When I equals 3, this is negative 20 over n. So for this first sum, we can use this first law. So this is going to be n times negative 20 over n. That's what that first thing is going to give you. For the second one, we can think about this 32 over n squared as a constant times something which depends upon I. So the 32 over n squared can be pulled out front. And we're just left with this thing. And this thing satisfies that form, that we use that formula down there for the last guy. So this first thing, that n times negative 20 over n is just negative 20. This second one is 32 over n squared times n times n plus 1 over 2. The n's cancel. And so this becomes limit as n goes to infinity, negative 20 plus 32 over 2 is 16. And 16 times n plus 1 is 16n plus 16 all over n. Sorry, I skipped a couple steps going from here to here, I guess. Any questions about what I've done so far, simplifying this thing down to here?
Is this for, that's for right endpoint approximation,
Yes.
right? Because for left endpoints, you would have to put I minus 1.
Exactly.
Right, okay.
And I mentioned earlier, whenever you're trying to turn an integral into a sum, using right endpoints will make these formulas a lot simpler. So just use right end. Yeah, I will never ask you to do this sort of thing with right endpoints. By the way, also, again, as I mentioned, this question is too long to be a quiz question. It would be like a written assignment question if I asked you anything like this. But, yeah. But yeah, so the key thing here is that these summation formulas can allow you to turn this ugly sum into a limit that we can evaluate. And now what we've got to do is we've got to find this limit. Well, the limit of negative 20 is just negative 20, right? That's not a problem. This thing is going to be the problem when finding the limit. If you remember how to find the limit of a fraction, and then goes to infinity, you just look at the first biggest term on the top, biggest term on the bottom. 16n over n is just 16. So this thing will give you negative 20 plus 16 equals negative 4. Any questions about what I did here? Any of these steps that people find confusing? Again, I know that this, anyway, one thing I want to mention about this particular topic is, again, this is the hard way of doing integrals, by writing them out as sums and using sort of sum laws to try to simplify them. Laws of summation are sort of annoying things to have to work with. They get formulas which are fairly annoying as you're working through them, and then you still have to take a limit at the end. And this is actually a pretty simple integral to do. The thing inside is just 2x minus 1. And this is how complicated the problem is. So there was a time at which all integrals were done this way. Every time someone was trying to compute an area, they did it by turning it into a limit of some formulas and then doing this lengthy procedure to it. But this is definitely by far the hardest way of doing integrals. It was the way people did it for about 1,000 years, but it is definitely not an easy way of doing it. Are folks going to be okay if I slide this and cover this stuff up? Yeah? Okay. Because the other thing I want to mention about this method is the integral we've just evaluated is this guy, right? This particular integral has a much easier way of evaluating. Right? With this particular one, if we actually sketch the graph of this guy, it looks like that. This is what the graph of y equals 2x minus 1 looks like. And if you want to calculate its area, sorry, those line should be there and there on the x-axis. If you want to calculate its area, you can do it just using two triangles. This graph is a straight line. So if you want to calculate this integral, there's a much easier way of doing it. Calculate this area 1 above the x-axis, calculate the area 2 above the x-axis, and subtract it. All right? And if we do that, this area above is a half times the base times the height. The height here is 3, the base is 1.5, multiply it by a half. I'm annoyed about the way the boards are set up in this classroom. I'll do it over there. I don't have it. So, the first area is a half times the base, which is 1.5, the height, which is 3. That's for this triangle. The base of this guy is 2.5, the height is 5. 1.5 times 3 is 4.5. 2.5 times 5 is 12.5. 4.5 minus 12.5 is -8. So we get the same answer, -4, by a much faster procedure. Right? This graph can be sketched really quickly with your graphic calculator, even if you don't remember how to sketch the graph of linear functions. Once you have this graph, you can recognize this is a triangle, this is a triangle. Again, the hardest part really is just measuring this, and measuring this, and measuring this, and measuring this. And again, those shouldn't be difficult tasks to do. I mean, they're not trivial, but they shouldn't be difficult either. So the key thing is that, anyways, this stuff I already talked about, these two last paragraphs here I already talked about last class. The idea that when you're calculating an area, or when you're calculating an integral with a function that goes below the x-axis, any area below counts negatively. So the a2 down here counts negatively. But the key thing is that it is much easier to evaluate integrals by sketching the graph and calculating the area than it is by using that method, using sums on the last slide. The only problem is that the sketching the graph and calculating the area method only works if the graph is either a rectangle, a triangle, or a circle. If it's anything more complicated than that, it's a parabola. If it's a cubic function, if it's a sine, if it's a cosine, you cannot use any of those area formulas that you learned in high school to do that. Now, the method using sums on the previous slide will work for parabolas. It will work for cubic functions. It won't work on its own for sines and cosines. You need something even more complicated for sines and cosines. But it is definitely not the best way of doing things. And I'm not going to do the area of a parabola using that method. I'm not going to do the area of a cubic function using that method. The book does, if you want to have a look at what the book does. But the point of that one example I did do was just to show you how complicated that method is and how much we want to avoid using it at all costs, pretty much. And how much easier it is to just calculate integrals using areas of triangles. And the fact that they give you the same answer, right? This gives you -4. Using the triangles also gives you -4. Any questions before we move on? Okay. So, yeah. So I've done this example already. I'm talking about how to evaluate these integrals using area. So what I'm going to move on to next is this thing that's called the midpoint rule. And the idea is that there are some integrals whose areas we can evaluate, right? Like these ones with this triangle. There are some integrals who we're going to figure out how to do later. There is also a third category of integrals, which are those integrals which actually you can't do using any method. There are integrals out there that there is just no method of evaluating directly. And in those situations, the best thing you can possibly hope to do is to estimate the area under the integral. you cannot really hope to ever actually get it exactly. The best you can do is get an estimate that's correct to like 10 decimal places, which for most purposes is pretty darn good, right? Like, there's very few situations in which having 10 decimal places of accuracy is not good enough. But sometimes it's the only thing we can do. And the first method we're going to learn to estimate value of integrals is actually something we've already done. Right? In section 5.1, we were estimating areas. That same method can be used to estimate values of integrals. It just has a special name in this case. And the special name is what's called the midpoint rule. So we can use the midpoint rule, which is based on the method we've done in section 5.1, to estimate the value of integrals like this. And what the midpoint rule says is just to get a good approximation, to get a good estimate, you should always use a Riemann sum with midpoints. So whenever you're trying to get a good estimate of an integral, you should always do that procedure we did last class using the rectangles and everything like that. But you should always use midpoints to get the best possible estimate. That's what the midpoint rule says. So if you ever see use the midpoint rule to do this, think about it as saying use rectangles with midpoints to do this. Right? The midpoint rule is just saying using rectangles with midpoints. And again, a Riemann sum is just a fancy word for that method that we did in section 5.1 where we estimated areas of rectangles. If you see the word Riemann sum, that's also another sort of indication you should be using those rectangles. So I'm just going to do an example of something we can do with the midpoint rule. So here we want to use the midpoint rule to estimate the integral from 0 to pi over 2 of cosine to the 4th x dx. So the idea is whenever we're using Riemann sum, any sort of Riemann sum, the first step is always to think about the integral we're dealing with, which goes from 0 to pi over 2, and divide it into pieces, right? Here we want to divide it into 4 pieces. Remember, n always represents the number of rectangles we're using. So we divide it in half at pi over 4. But pi over 4 is half of pi over 2. Halfway between pi over 4 and pi over 2 is, well, halfway between quarter and a half is 3/8. This is 3 pi over 8. Halfway between pi over 4 and 0 is pi over 8. If you have a hard time finding this guy, one of the easy ways of doing it is first find this guy. What's half of pi over 4 is pi over 8. And then just be like, this one is this distance past pi over 4. It's going to be pi over 4 plus pi over 8, which gives you 3 pi over 8. Another way we can find these guys is using the formula we talked about earlier, where delta x is b minus a over n, xi is a plus I delta x. Those formulas will also work to find these guys. Right, delta x is pi over 2 minus 0 divided by 4. That gives you pi over 8 for your delta x. This is a, which is 0 plus 1 delta x, gives you pi over 8. A plus 2 delta x gives you pi over 4. A plus 3 delta x gives you this. Okay. So then we've got these intervals. The midpoints, we're doing the midpoint rules, we're using the midpoints of the intervals, are pi over 16, 3 pi over 16, 5 pi over 16, and 7 pi over 16. Again, you can get these by just taking the average of these two guys. 0 plus pi over 8 divided by 2 is pi over 16. Pi over 8 plus pi over 4 is 3 pi over 8 divided by 2 is 3 pi over 16. Pi over 4 plus 3 pi over 8 is 5 pi over 8 divided by 2 is 5 pi over 16. So, yeah. And then, once you've got each of these numbers, then you've got to plug each of these numbers into this function, right? Because these are your sample points. To find the height of the rectangle, you always take the sample point, plug it into this. So here we're going to have cosine to the 4th pi over 16. Here we're going to have cosine to the 4th 3 pi over 16. Here we're going to have cosine to the 4th 5 pi over 16. And here we're going to have cosine to the 4th 7 pi over 16. If anyone wants to, actually, you know what, I'm going to do, if folks can actually calculate these things on their own, I'm going to divide up the work. Who wants to calculate what goes into 4, 5, or 16? Anyone?
There is a sequence function that allows you to do it automatically, like using a Riemann cell.
Oh, on the graphing calculators?
Yeah.
I have not seen this before.
Okay.
So this is a good thing. This is a good thing. It means that that means that the rest of the work that I have to do on the board. Sadly, I can't do it today, but maybe if you can show it to me after class, I can go over it. Or if someone wants to compute this thing pretty quickly using that sort of thing, that's also great. But yeah, no, I was going to say having calculators that can do this for you is great because doing it yourself takes a lot of time sometimes. I'm in degrees. I want to be radians. Make sure you're in radians, of course, if you're doing this.
Are we bringing graphing calculators to this now?
Yes. Yeah. Yeah. Yes, because graphing calculators can't do any actual calculus for. Oh, wait, did I just do? Yes, sorry, this thing has to put to the fourth. It was going to be 0.83 to the fourth. So 0.98 to the power 4 is 0.92. This was 0.9095. And this one. If anyone has a different answer than me, please let me know because I could have made mistakes. Oh boy, this is really small. 0.0014. Anyways, so these are all the heights that it's a rectangle. This rectangle will have this height, this one will have this height, this one will have this height, this one will have this height. So if you want to calculate the area, you've got to take all those heights, multiply each of them by delta x, by the width, and add them up. So you'll have area 1 plus area 2 plus area 3 plus area 4 will be 0.92 times pi over 8 plus 0.47 times pi over 8 plus 0.095 times pi over 8 plus 0.0014. And if you add those up, so 0.36 plus plus 0.18 plus 0.095 times pi over 8, 0.037 plus 0.00055. And if you add those up, 0.36 plus 0.18 plus 0.037 plus 0.00055, 55, whoops, 0.36 plus 0.18, 0.037, 0.00055, 0.58. So the area here is approximately 0.58. Yes?
Why are you multiplying by pi over 8?
Because you always have to multiply them by the width. Right? If you multiply, okay, yes, sorry. Sorry, I should have actually shown more work on the board. This distance is the width of each rectangle. Right? Here you're calculating rectangle with this width and that height. Here it's going to be this width and that height. Here it's going to be this width and that height. Here it's going to be this width and that height. And you know what I'm also going to talk, anyways, the other thing I'm realizing, this would be shown better if I actually had better board space, a better relationship between the screen space and the board space, which I have in the other classroom. So what I may actually do is I may try to see if we can move the Thursday's class to the other classroom as well. And if we can, then we don't have to worry about it, it'll all be in the same room. So I'm going to talk to someone after class today about that, potential moving this one to the Thursday classroom, and then this will become better shown, because when I'm in that classroom, I don't have the same problems I do when I'm in here. And yeah, I'm definitely having a harder time organizing myself with the two different board spaces that are widely separated and screen space in the middle. So, yeah. Any questions about examples? Yes?
How is it that this would work with the limit like the last one's would, the limit of the sum?
Oh, the reason is because what you will get, thank you for asking this. Yeah, if you do this thing, what you will get is something like this. You'll get this in the sum. And the thing is, there is no summation rule for dealing with the cosine to the fourth. Right? There's a summation rule for dealing with I. There's a summation rule for dealing with I squared. There's no summation rule that tells you what you can do if there's a cosine to the fourth in there. And that's the problem, is there's no formula for this guy. Right? The reason this worked is because this thing, you could simplify until it was just sum I equals to n of I. And there is a formula for that. And again, the way you simplify it in this case is 32 over n squared you could pull out front. Here, cosine to the fourth is not, it's not cosine to the fourth times this, it's cosine to the fourth of this. Which means you're not allowed to pull the cosine to the fourth out front in the same way. So that's the big reason. And we will see this also with integrals, is that this procedure of pulling something out front of the integral is going to be sort of an important thing to make integrals easier to evaluate. And the real question is, once you pull that thing out front, what is left once you pull that thing out front? If the thing that's left is just an I, or it's just an x in the case of integrals, it's easy to integrate. If the thing that's left is more complicated than that, like the cosine to the fourth, then you have to worry about using more complicated methods of integration. So you could turn this into a limit of a sum. The problem is that this sum you can't evaluate easily. Yeah? Any other questions about this? Okay. Okay. So the last thing in section 5.2, and I know section 5.2 has been a fairly, it's been a longer section than anything else in chapter 5. That's because there's a lot of stuff in there, and it's difficult. Some of it's difficult stuff to understand what's actually going on. Although there isn't that much you can do right now. The last thing I'm going to talk about in section 5.2 is some properties of the definite integral which are useful for evaluating integrals. And one thing that's going to come up is there's going to be a relationship between the integral from 0 to 2 of a function, the integral from 2 to 4 of a function, and the integral from 0 to 4 of that function. How many people here think they know what that relationship is between those three things? How many people here have learned this sort of thing at one point in time and forget it? And how many people have never learned this sort of thing or don't know anything about it? Okay. So the key thing when you're talking about those sort of relationships is actually to understand. Just check that that's the first. I think that's actually the second slide here. So I'm going to talk about that particular relationship later. The first thing I'm going to talk about actually are what are called the linearity properties of integrals. They're properties which allow you to sort of simplify integrals before you evaluate them. Sort of similar to what I did with this thing with the summation, sort of trying to simplify it before I actually used a formula to add it up. And these linearity properties are as follows. The first one says that if we want to integrate a number, c here is always represents a number. It's not a variable. It's like a constant like 10 or pi or 17.5. What this is saying, if we want to integrate c, is that we have a function which is constant, which is always, like y equals c is a straight line across like this. And we want to find the area under it between a and b. Well, that region is just a rectangle. Right? This area we're trying to calculate is just the area of that rectangle. What's the area going to be? It's going to be this distance times the height. So it's going to be the height, which is c, times the length of the rectangle, which is b minus a. So this formula is useful for evaluating any integral of a number. So if you have the integral from 2 to 4 of 6, we can evaluate it using this formula. Integral from 7 to 12 of 23, we can evaluate it using this formula. This one here says if we have a constant times something, that constant can be brought out front of the integral sign. So it says if we have, for example, the integral from 2 to 3 of 3x squared, that 3 that's in the integral can be brought out front. It's going to be 3 times the integral of x squared. So what this means, if we know how to integrate x squared, we know how to integrate this guy. We can just bring the 3 out front and then do this guy. This property is sort of like one of the most important properties when working with integrals. It's used like all the time. Constants can be brought out front. Again, where this comes from the fact that the integral is just an abbreviation for that limit of the sum symbol. And that same property exists for the sum symbol. So it'll also exist for the limit symbol. And I don't know if you remember that example I did where it's like the sum of 3i squared, you can bring that 3 out front. Same thing's going on here. Same thing will happen if you have f of x plus g of x. If two separate functions add together, we can integrate them separately. We can integrate the first one plus what we get when we integrate the second one. Drop that eraser. So that second property says, for example, if we have the integral from 2 to 4 of x squared plus x cubed dx, it's the same thing as the integral from 2 to 4 of x squared plus the integral from 2 to 4 of x cubed. And similarly, if we did the same thing but without the instead of a plus, we had a minus, this would become a minus. And again, I sort of illustrated these same properties earlier with the sigma, the summation symbol. They work the same way for integrals. So what these integrals can allow you to do is to evaluate complicated integrals using integrals that we already know. So for example, let's suppose using limits of sums or something, we figured out what the integral of e to the x is. The integral from 1 to 3 of e to the x is e to the 3 minus e to the 1. Now we want to evaluate the integral of this guy. And the idea is to evaluate that integral, we can just use those properties up above. If we want to take the integral from 1 to 3 of 2e to the x minus 2, we can say, okay, we've got something minus something else, we can integrate them separately. This guy, we can pull that 2 out front. This guy is just a rectangle, right? This guy is like this thing up here. So its area is going to be 2 times 3 minus 1. And then we know what the integral of e to the x is. We've said here that the integral from 1 to 3 of e to the x is e cubed minus e to the 1. So this whole thing gives you 2 times e cubed minus e to the 1 minus 2 times 2. And that's what the integral will give you. That's what the area will be under the graph of that guy. And again, if you wanted to, you could simplify this. In this course, I'm not going to worry too much about your simplifying your final answers. What I'm really, as long as you get an answer that has no integral sign in it, I'm not going to care too much about what you do with this thing. You know, like, write it out, that's fine. Yeah. Just keep going until there's no more integral sign. That's the important part. Any questions about this exam? Kind of hold that. Here, I can do this again. That helps. Here's another example that we can do using those linearity properties. Suppose I want you to evaluate this integral here. I'll do it over here. Now the key thing is that if we sketch the graph of this guy, the graph is going to look like that. That's not a shape that we know how to calculate the area of. Right? This is some sort of J-shaped thing. So I'm like, I look at the graph, I'm like, okay, I can't calculate the area using the graph. But what I can do is I can notice that there's something minus something else. So we can split it up as two separate integrals. Then, if we look at this shape, what does this shape look like? The function y equals x is just a diagonal line. So if we're going from -5 to 5, we're really just talking about, here, I'm going to, the area of two triangles. This one, no, I won't put the minus sign between them, so that might be confusing. This one, if you sketch the graph of it, is a semicircle. So we can also calculate its area. Now, once you have them together like this, when you sketch the graph, it didn't look like it, it was just going to be your J. But it turns out that it was actually a linear function minus a semicircle function. And both these guys, you can calculate areas. So let's call this thing A1, A2, and this guy A3. So if we're calculating the areas, the first integral is going to be A1 minus A2. And the second integral is going to be A3. A1 is a half times the base, which is 5, times the height, which is 5. You measure that triangle. A2 is actually the same thing. In fact, if you look at this picture, this triangle and this circle are actually exactly the same size. So this area above, this area below will actually cancel each other out when we do the integral. A3 is a semicircle. Its area is going to be 1/2 times pi times the radius squared. The radius of this thing is 5. So these guys will cancel. It'll give you -25 over 2 pi. This thing, 5 squared is 25. 1/2 times 25 is 25 over 2 pi. And these guys will cancel. And that is the value of the integral. So the key thing is that even if you sketch the graph of something and it doesn't necessarily look like, you know, a nice graph that we know how to calculate the area of, sometimes you can split it up into things which do have nice graphs and calculate the area that way. Any questions before I move on? Okay. Another set of properties about integrals are properties that deal with these limits of integration. One property says that if we switch the limits of integration, we have to multiply the integral by -1. We have an integral from b to a, we want to make an integral from a to b, we've got to put a -1 in front. The reason for this is if we switch the direction of the integral, all these little delta x's in here will suddenly become all negative. So it's going to make everything end up being negative. I'm not going to sort of go through the algebra to show you that. I'm just going to say, trust me, if you switch the order, it'll become backwards, and that'll make it negative. Another property is the fact that if we want to integrate a function from a to c, one way we can do it is integrate it from a to b, and then integrate it from b to c and add them together. So if we want to calculate the red area from A to C, right, one way we can do it is first calculate the blue area, and then calculate the green area. So if you want to integrate from A to C, you can do it by integrating from A to B, integrating from B to C, and adding those two things together. So the example I showed on the first slide where I had an integral from 0 to 2, an integral from 2 to 4, and an integral from 0 to 4. The idea is the integral from 0 to 4 is the one from 0 to 2, plus the one from 2 to 4. Basically, the area between 0 and 4 is the area between 0 and 2, plus the area between 2 and 4. So again, these things are also going to be useful to evaluate integrals. So if we have something like example 10 here. Here we know, there we go. We know what the integral from 1 to 5 is. The integral from 1 to 5 is 12. The integral from 4 to 5 is 3.6. And they want you to find the integral from 1 to 4. Well, the key thing is this. Right? The integral from 1 to 5 is the same thing as the integral from 1 to 4 plus the integral from 4 to 5. The integral from 1 to 5 is 12. The integral from 1 to 4, that's what we're trying to find. And the integral from 4 to 5 is 3.6. So if we want to find this guy, all we want to do is subtract 3.6 from both sides. And so we'll get that the integral from 1 to 4 is 12 minus 3.6, which is 8.4. Any questions about this idea? Okay. Last slide in section 5.2 is what's called the comparison properties. Comparison properties are properties that allow you to compare one integral to another, say which one's going to be bigger. All these properties are really obviously true if you can visualize what's going on. And I always want to say, visualizing what's going on is important in a lot of these situations. Understanding when we see this sort of symbol that we're talking about in area is an important thing to keep in mind. So the first one says that if we have a function which is bigger than or equal to 0 for all x between a and b, then the integral of that function will also be bigger than or equal to 0. What this is saying is it's saying this thing. If we sketch the graph of something, and between these two numbers, right, between a and b, this graph is above 0, then this area will be positive. Right? There's no negative area here. There's no area below the x-axis because the function is bigger than 0. So that makes the area positive. The area here is also bigger than or equal to 0. The second thing says that if we have one function which is bigger than another function, then the area under the first function is bigger than or equal to the area under the second function. So this one says that if we have two functions like that, actually I'm just going to make this one not below 0 so it makes the picture look a little bit nicer. Right? So f of x is the top one, g of x is the bottom one. And we have a and b. Then the green area, which is this integral, the area under f of x, that green area will be bigger than this blue area, the area under g of x. And the last property says that if we have a function whose graph is between a number capital M and a number lowercase m, so it's above lowercase m, it's below capital M, then if we want to measure this red area, we can compare it to two things. We can compare it to lowercase m times b minus a. Lowercase m times b minus a is that green area, right? The height is lowercase m, the width is b minus a. It's going to be bigger than the green area, but it's going to be smaller than this blue area. This blue area is capital M times b minus a. Height capital M times width b minus a. So basically what this is saying is that this red area is bigger than the green area, it's smaller than the blue area. And this always happens when we have a function between one number and another number. So all these properties are really easy properties to see if you sketch the graph of the function in question. And if I'm ever going to ask you to use these properties, I will always give it to you in sort of the graphic calculator section of your test. In a section where I'm going to say, pull out your graphic calculator, use your graphic calculator to do this. One thing I'm going to mention now about the way I do tests, which I haven't mentioned before, is that there's always some parts of the test where I say, please use your graphic calculator to do this. Other parts of the test where I say, show all your work. And which means you can use your graphic calculator to check your work on the other sections of the test. But if you don't actually show the steps that you use to get to your answer without the graphing calculator, then I can't give you full credit. So, yeah. Any questions about sort of these properties and what they mean? Again, when you look at them in the textbook, the way they're written out like this, sometimes they're hard for you to understand. But if you sort of understand them in terms of these visual pictures, they should make a lot more sense. So the idea is if I want you to use these comparison properties, what I'll usually get you to do is to say, explain why this thing is true. So here's here's two statements. So let's say I'll ask you to explain why this guy is true. Explain why the integral from 0 to 1 of the square root of 1 plus x squared dx is less than or equal to integral from 0 to 1 of 1 plus x dx. Well, what you do, if you want to explain why this is true, is to pull out your graphing calculator, sketch the graph. The first one, the graph is going to look like this. And the second one, the graph is going to look like this. The graphs will be very close to each other, but the second graph, so the top graph is square root 1 plus x, and the bottom graph is square root 1 plus x squared. Right? Yes, that looks. Oh! Yes, that's right. Anyways, the key thing is, and 0 is here, 1 is here. Right, so we're talking about between 0 and 1. So if you sketch those graphs, you can see that the green area, right, the area on the right, is bigger than the blue area. Sorry, the blue area I haven't sketched yet. The blue area is this one. They both end here. Right, the area under this guy is bigger than the area under this guy. So if I ask you to verify this thing, what I really want you to do is sketch the graph and show you that this graph is above this graph. And say something like, since square root 1 plus x is above square root 1 plus x squared, the area under square root 1 plus x is bigger. This last one is a little bit harder, but it uses the same principle. So here I want you to sketch the graph of cosine x. The graph of cosine x looks like that. Pi over 6 and pi over 4 are here. So what I'm trying to measure is I'm trying to measure that green area. I want to show that that green area is bigger than this thing, whatever that thing is, and is smaller than this guy. Well, the idea is really what I'm comparing it to is two different rectangles. I'm comparing it to the red rectangle, and I'm comparing it to the blue rectangle. So, the red height, the height of the rectangle comes from here, pi over 4. So the red height is cosine pi over 4, which is square root 2 over 2. The blue height, right, comes from here on the graph. That's pi over 6. So the blue height is cosine pi over 6, which is square root 3 over 2. And if we measure this width is pi over 4 minus pi over 6, which is 3 pi over 12 minus 2 pi over 12, which is pi over 12. So the height, square root 2 over 2 here, square root 3 over 2 here, the width is pi over 12. So if we want to calculate the red rectangle's area, its area is going to be the height times the width. Square root 2 over 2 times pi over 12, which is square root 2 pi over 24. So that's where this number comes from. Is the width of that rectangle times its height. This number comes from the blue guy. Here we're going to have square root 3 over 2 times pi over 12, which gives you square root 3 pi over 24. So the idea is if you want to verify this inequality, you can sketch the graph of cosine x. These two numbers, if I'm ever comparing something to two numbers, those two numbers will always be a rectangle that's bigger than the graph, and a rectangle that's smaller than the graph. And again, that blue rectangle is basically the smallest possible rectangle that's bigger than the graph. The red one's the smallest possible rectangle that's smaller than the graph. We just calculate those two areas, and those two areas should equal these two numbers in this sort of situation. Any questions about this? Okay, so that's going to be it for the portion of the class before the break. So take a 10-minute break now. Again, I'm definitely behind where I was expecting to be. That's okay, because I realize that I can do the second half of 5.3 on Tuesday, which is what I'll be doing. So take a 10-minute break. After the break, I will start section 5.3. I will not finish it. And then we'll do the rest of 5.3 on Tuesday. So yeah, take 10 minutes. Come back at 10 minutes to 1.